All right, welcome back to another lecture. In this video, we will be discussing section 3.7, which is about comparing two numerical variables. In the previous section, 3.6, we talked about kind of reimagining the way that we talk about hypothesis tests and the way that we talk about comparing data sets. Instead of talking about comparing two data sets, what we could talk about is, that we might have a data set that contains more than one variable in it, that has, two or more variables, and then we might want to compare those variables to one another. And so we talked in 3.6 about how if you have two categorical variables, you're going to probably make some kind of contingency table. If you have a categorical variable that you're trying to compare to a numerical variable, then you'll probably want to split the columns and then compare the means of those two columns, okay? If you want to compare two numerical variables, then you make a scatter plot. We talked about that last time. And then from the scatter plot, you can get kind of an eyeball for whether or not there is a linear correlation between the variables that you're comparing. However, we want to have a mathematically rigorous way for deciding when we really do have a correlation and when we don't. And so there is a hypothesis test for that. And so this is the last hypothesis test that we're going to introduce in the course. In 3.8 and 3.9, we'll talk about the same hypothesis test that we've already discussed for comparing means and proportions, but we'll just rephrase them in terms of independence. But in this section, we have a brand new hypothesis test, and we're going to call it the linear correlation test. If we decide that our variables have a linear correlation, then we can actually compute the line that best describes the data. We'll call that the best fit line. And we can use that line to make predictions about values that may not necessarily even be in the data set. So we're going to cover all of that in this section, all about linear correlation, comparing two numerical variables. Okay, the first step in deciding whether or not we have a linear correlation is to compute what's called the linear correlation coefficient. And the symbol for that is the letter R. This is a new statistic that we haven't discussed before. And as you can see, it's a really nasty calculation. So just to kind of comment on this calculation a little bit, right? So we're going to be comparing one set of numerical variables, okay, which we'll call our x coordinates, to another another numerical variable, which we'll call our y coordinates. And what we're doing here is we're computing basically a z-score for our x coordinates and then a z-score for our y coordinates, right? In order to do that, we first have to get the standard deviations, the means. Doing all this by hand would take a lot of work. Once we have the standard deviation and the mean, we would have to compute the z-score for each observation in the data set, multiply them together, multiply the z-scores for our x coordinates and our y coordinates together, and then add them all up. It would just take a very long time to do by hand. So of course we're not going to do it by hand. We'll let technology do this for us. Some properties about this linear correlation coefficient, though. It's always the case that R is between -1 and +1. If R is really close to +1, then there's a strong positive linear correlation between the variables. If R is close to -1, then there's a strong negative linear correlation between the variables. If R is close to 0, then a linear correlation does not exist. That doesn't mean that there's no correlation at all. It just means that there's not a linear correlation. So let me show you what I mean with some pictures, right? In A, we have a perfect positive linear correlation, right? R would be equal to 1 there. In part B, we have a pretty strong linear correlation. R might be, something like 0.9. In part C, we have a moderate positive linear correlation. R would be close to something like 0.4. And then we have the same thing for the negatives, right? A perfect negative linear correlation in part D. Part E is a strong negative correlation. Part E is a moderate negative linear correlation. And then part G, we see there's no correlation whatsoever here. right? So R would be close to 0. For H, on the other hand, there seems to be a correlation, but it's just not linear. Okay, there is a pattern there. It's kind of like a U-shaped pattern, but it's not linear. And so R would still be close to 0 in the case of part H. Again, R is the linear correlation coefficient. It only tells you if there's a linear correlation. Non-linear correlation is beyond the scope of this course, so we're not really going to talk about it. But we will, discuss where we have linear correlations and when we don't. So again, the calculation of R can be pretty nasty. So we're just going to let technology do that calculation for us. You can click on this app to take you directly to the app that we're going to use from artofstat.com, but I'll show you how to get there just from the website directly. So let's do one of these. Number 1 here says, calculate the correlation coefficient R for the relationship between absences and final grade below. To do this, we will go to Art of Stat, and we're going to use the linear regression app. And again, I'll show you where to find that. But it'll do that calculation for us, and then we'll be able to tell approximately how much R is. So let's head over to Art of Stat. So here in Art of Stat, this is the home page. If you click on Web Apps up at the top, then you can scroll down, and we want to use the linear regression app. So it's here under Association, Correlation, and Regression. We want to use the linear regression app to do all of our stuff in this section. We don't have we're not using a textbook example here. We'll just enter our own data. And you can label the variables here. We're comparing, in this case, absences and final grade. We want to see if there's a correlation, right, between the number of times you miss class and your final grade. So I'll just enter the data. You could also, there's an Excel spreadsheet that we're definitely going to want to use to enter our data on a few examples later on in this lecture, because they're very large data sets. In this case, this data set's pretty small, so I'm just going to punch these in. And then hit Submit Data, and it'll actually give you a nice little scatter plot there, which is pretty nice. You can see the correlation coefficient here in the model summary at the bottom of the page, right? Our correlation coefficient R, in this case, is about negative 0.944. And that's that. So let's write it down. So R is approximately negative 0.944. Okay, and that's all there is to it. So that's how you calculate a linear correlation. In this case, this would suggest a fairly strong negative correlation between these variables, and I think that's pretty clearly seen in the scatter plot, right? As the number of absences increases, the final grade decreases. Okay. So let's talk about how to test whether or not that's true. I mean, we can calculate this linear correlation coefficient to get a sense for how strong the correlation, but the question is, like, exactly how close to 1 or negative 1 does R need to be in order for us to conclude definitively that there is a linear correlation between the variables? And that's where this linear correlation test will come into play. The sample correlation coefficient is R, as we have already introduced. The population correlation coefficient is this letter. It looks kind of like a P, but it's kind of slanted. You would write it kind of like this. Okay? And that's the Greek letter rho. If we were writing this on lined paper, right, it would look kind of like that. So this is the Greek letter rho. So as usual, we use this statistic r to estimate this parameter rho. Okay, we can't be 100% sure that rho equals r, and so to test whether two variables are linearly correlated, we'll run a hypothesis test. Okay, we'll use our sample statistic r, our sample correlation coefficient r, to run a hypothesis test for our population correlation coefficient rho. Now, if there's no linear correlation, then our sample correlation coefficient would be 0, and so our population correlation coefficient would be 0 as well. So if there's no linear correlation, rho equals 0. Otherwise, rho does not equal 0. Okay, if rho does not equal 0, then there is a linear correlation. So those are the hypotheses, right? Our null hypothesis is that rho equals 0. Our alternative is that rho does not equal 0. It is possible to run a left-tailed or a right-tailed test here, but art of stat does not allow for us to do that. So we'll just stick to two-tailed tests, and that's fine because we can tell if the trend is positive or negative by looking at the scatter plot. Okay, so we don't really need to run a left-tailed or a right-tailed test anyway, so we'll just stick to the two-tailed test. We'll state our hypotheses in step 1 as usual. In step 2, we'll gather our sample evidence. In this case, our sample evidence is the sample correlation coefficient r, which of course we're just going to let art of stat do for us, as we saw a second ago. And then we'll get the p-value. We get the p-value from the same place that we went to get the correlation coefficient. The only thing we need to do is to make sure to check the box that says show standard errors and p-values, and that will get us the correlation coefficient. Or sorry, that'll get us the p-value for the test. It'll actually compute a couple different p-values. It'll compute a p-value for the slope, and it'll compute a p-value for the intercept. The p-value we want is for the slope, okay? And that might seem a little bit confusing because you might be thinking, wait, but we're not testing slopes, we're testing correlation coefficients. But for reasons that we're not going to take time to discuss here, testing the correlation coefficient rho is equivalent to testing the slope of the best fit line, which we're going to talk about later. We're going to talk about the best fit line and slopes and all that stuff. But those are equivalent things, and if you want to know more about why they're equivalent and how the p-value is being calculated, you can follow this link here. Okay. Once we've made our decision, we'll write a conclusion, which says what our decision means for the alternative hypotheses. One thing that I want to talk about before we run examples is that if rho equals 0, then that means there's no linear correlation between the variables. Another way to say that there's no linear correlation between the variables is to say that the variables are independent, right? If there's no correlation, then the variables don't affect each other, so they're independent, right? Therefore, an equivalent way to write the hypotheses for this test are to say variable 1 and variable 2 are independent variables for the null hypothesis, and for the alternative, variable 1 and variable 2 are dependent variables. If we reject the null hypothesis in this test, then that means that there is a linear correlation, right? We would say there's evidence to support the claim that there's a linear correlation, or in other words, that the variables are dependent. Okay? Not rejecting the null hypothesis means that there's not sufficient evidence to show a linear correlation or to show that the variables are dependent. Okay? So let's run, I think I've got a couple examples, yeah. So example 2 here says, the number of absences that a student had is listed together with their final grade in the course. And it's the same data set that we were just looking at a second ago. It says, determine if there is a linear correlation between absences and final grade. The null hypothesis would be that there is no correlation, right? That rho equals 0, no linear correlation. The alternative would be that there is a linear correlation. Rho does not equal 0. The sample evidence that we have in favor of the alternative hypothesis was that sample correlation coefficient that we computed in example 1, right? We got r equals negative 0.944, which seems to suggest a pretty strong correlation. The only way to know for sure if that's strong enough is to compute the p-value. So we're going to go to art of stat, and we're going to run a linear regression test. And of course you have to enter the data right into that app. But then once you've done that, we can get our p-value. So let me take you back over to artofstat.com so we can see what this looks like. So we're still here with the same data set that we've already entered in. By the way, you get some pretty nice descriptive statistics up here. Those might be helpful or useful for certain things. It is not helpful to compare final grade to number of absences. Obviously, your final grade is going to be more than the absences you had in the class, unless you did really terribly in the class. But the question you might have here is, how do we get the p-values? Because there's no p-value in the results here. So what you have to do is over here under regression options, you have to click on this little box that says show standard errors and p-values. And when you do that, then this table expands and you get standard errors, test statistics, and p-values. This is the p-value for the intercept, right? This is if you run a hypothesis test to see if the best fit line is a good model for the data, then this p-value tells you whether the y-intercept is a good fit. That's not the one we want. We want this one. This is the p-value for the slope, okay? So we want the p-value for the slope, 0.0014. Let's write that down. So our p-value is 0.0014. Okay, we can use that p-value now to make a decision. We would say 0.0014 is less than 0.05. So reject the null hypothesis. Okay, in other words, if we assume that the population correlation coefficient is 0, then there's only a 0.0014 probability of obtaining a sample correlation as different from 0 as the one that we computed. That's a really small probability. So maybe we shouldn't assume that H null is true, right? So we reject it in favor of the alternative. So the alternative says rho is not 0. In other words, there is a linear correlation. And so that's what we would say in conclusion. Right? We would say there is sufficient evidence to conclude that there is a linear correlation between absences and final grade. Okay, another way to say that is that absences and final grade are dependent variables, right? Maybe I'll put it in quotes. Absences and final grade are dependent variables. right? Your final grade depends on how many absences you had in the class. It's not uniquely determined by the number of absences, but the number of absences does affect your final grade. Okay, so your final grade is dependent on how many times you missed class. So that's the conclusion of that test. Let's do another one. Okay, you can go ahead and pause the video and run this one yourself. It says the data below describe the monthly income of 8 people and the number of times they eat out each month. Determine if there's a linear correlation between income and eating out. Use the 0.05 level of significance. Okay, let's head over to Art of Stat to run this. Let me grab a new linear correlation or linear regression. We want to enter our own data. This time we're comparing income and meals eaten out. And we can just enter the data. You could also copy and paste it from the Excel spreadsheet. But we don't have that much data here, so I'm happy to just type it in. Okay. Then I'm going to submit the data. Again, it kind of seems like there's maybe a negative correlation. This time our correlation coefficient is much smaller, right? Much, much smaller. So let's write that down. Let's write down our hypotheses and we'll write down our correlation coefficient. And then we'll run the test. So our null hypothesis, rho equals 0. Our alternative, rho, not p, rho. Rho does not equal 0. Okay. Correlation coefficient was R equals negative 0.297. Now that doesn't seem quite as different from 0 as the previous case, so maybe we're not going to be rejecting the null hypothesis here. The only way to know for sure is to run the test. So we go to Art of Stat, we go to Linear Regression, we enter the data. My tablet's glitching out a little bit, but we enter the data and then we get a p-value. Let's see. So to get the p-value, I'm just going to click on the box that says show standard errors and p-values. And it looks like for the slope, the p-value is 0.4746. 0.4746. Okay, so we're not going to reject the null hypothesis this time, right? That p-value is very large. This is our decision. (0.4746) is not less than 0.05. So do not reject. H null. In other words, if we assume that rho, that the population correlation coefficient is 0, then there's still like a 47% chance that we would get a sample correlation coefficient of negative 0.297. So that's just not unusual at all, right? That's a very high probability. And so we have no reason to suspect the null hypothesis. We're not going to reject it. And then we can write out our conclusion. Okay, we're not rejecting the null hypothesis, so there is not sufficient evidence to conclude that there is a linear correlation. Okay. There is not sufficient evidence to conclude that there is a linear correlation between what example was this? Between income, okay, between income and meals eaten about meals eaten out. Okay. You could also say that the variables are dependent, right? That income and eating out are independent variables, right? That isn't officially how we would state that conclusion. I mean, really, we would say there's not sufficient evidence to say that income and eating out are dependent, right? But that sort of implies that they are probably independent variables. That is, they have nothing to do with each other. So apparently it doesn't matter how much money you make. The number of times you eat out in a given, I think this was per month, yeah, the number of times you eat out in a given month, it doesn't depend on how much money you make. People are just going to eat out the number of times they eat out. Now, maybe if you make more money, the types of restaurants you go to might be a little bit different. But the number of times you eat out is not going to change depending on your income, at least according to this very small data set, right? So that's how the linear regression test works. Now, if a linear correlation exists, then we can calculate the equation of the line that best describes the correlation. And so I want to take a little bit of time right now just reminding us about how the equations for lines work, okay? So you might recall from your algebra days that the equation of the line is y equals mx plus b, where m is the slope and 0b is the y-intercept. The slope of a line, m, is the rise divided by the run, okay? And it's a measure of how steep the line is. It tells you how much y increases for every increase in x, okay? How much vertical increase there is for every horizontal increase. The y-intercept, 0b, is the place where the line crosses the y-axis. And what I would point out to you is that the x-coordinate for your y-intercept is 0 because it's where your line crosses. It's where your line crosses the y-axis. So if you've got a line, the place where it crosses the y-axis is the y-intercept. And of course, x would be 0 there. Okay, let's just practice identifying slopes and y-intercepts. Again, remember the form is y equals mx plus b, where m is the slope. So the slope is the thing that you're multiplying by x. In part A, the slope would be 3. The y-intercept is the other number, okay? It's the number that is not being multiplied by x. So in this case, the y-intercept would be -2, right? B equals -2. Or if you want to write it as a point, you could say it's the point 0, -2. Okay. In part B, don't be fooled. It doesn't matter what order these things are written in. The slope is always the thing that you're multiplying by x, in this case, -2. And it's important to take the sign that comes in front of the number, right? That's your slope, -2. And your y-intercept would be a +3 this time, okay? Or if you want to write it as a point, it would be the point 0.03. Well, okay, so we can write the equation of a line with a given slope and y-intercept. So let's say that you have a slope of 2 and a y-intercept of 5. The equation for the line would be y equals 2x plus 5. Or if you had a slope of -0.71 and a y-intercept of -32.4, then the equation for the line would be y equals -0.71x minus 32.4. And again, the order doesn't matter. You can rewrite these. You could say y equals 5 plus 2x. Or you could say y equals -32.4 minus 0.71x. Just make sure that you take the sign, the appropriate sign that comes with the number, right? Like, for example, y equals 3x minus 2 would be rewritten as -2 plus 3x. Okay. Okay. So that's the equation. That's how equations of lines work. Let's practice. Let's review a little bit about how to interpret the equation for a line. Number 6 here says the owner of a hot dog stand knows that the profit Y in US dollars generated by the sale of X hot dogs is Y equals 0.27x minus 9.24. How much profit would she expect by selling 50 hot dogs? Okay, so remember, X represents the number of hot dogs that she sells. Y represents the profit that she gets. If we want to know how much profit she gets by selling 50 hot dogs, we would replace X in this formula with 50, right? We would say Y equals 0.27 times 50 minus 9.24. And we can plug that into a calculator. Let's do 0.27 times 50 minus 9.24, and you get 426. So this comes out to $4.26. So if she sells $50, that's how much money she makes. I have no idea if this is accurate. I think I made this up, and it doesn't look very realistic to me, but that's okay. Part B, interpret the slope and the y-intercept. Well, the slope here is 0.27, right? What that means is that, remember, the slope is rise over run. It's how much profit we expect. In this case, it's the change in y divided by change in x, right? Y in this case is the profit. X is the number of hot dogs. So it would be the amount that our profit increases for every hot dog that we sell, right? So we expect our profits to increase by 27 cents, right? 0.27 is 27 cents when you're talking about dollars. We expect our profits to increase by 27 cents for every hot dog that we sell. It's becoming a trope, I think, in these lectures that you can hear my dog snoring in the background. I think my lectures put him to sleep, which I guess I don't really blame him for. Okay, the y-intercept here is negative 924. What this would mean is, remember the y-intercept is what you get when you plug in 0 for x. Okay? So if you plug in 0 for x here, of course you're just going to get negative 9.24. If x is 0, in this case that means that you didn't sell any hot dogs, right? So if we sell 0 hot dogs, we lose $9.24. Okay, so this is how lines work. This is how we interpret the slope and the y-intercept and how we make predictions. With that in hand now, let's let's talk about the best fit line. Okay, so the line that we want to use to describe the trend in our scatter plot should be the line that is the best fit for the data, of course. Now, what exactly does it mean for a line to be the best fit? That's somewhat open to interpretation, okay? But the line that we're going to use is called the least squares regression line. And this is widely considered the line of best fit because it minimizes the total squared distance between itself and the points in the scatter plot. Deriving the formula for the least squares regression line is beyond the scope of this course, but you can watch this video if you're interested, okay? Here is the equation for the best fit line. B1, our slope, is equal to R, which is our correlation coefficient, times our sample standard deviation of our y coordinates divided by the sample standard deviation of our x coordinates. And then the y-intercept, B sub 0, is the average of our y coordinates minus the slope of our line times the average of the x coordinates. Okay. Again, this would be a nasty calculation to perform. If for no other reason, then it's really hard to get R. So we're just going to use the same linear regression web app that we have used so far in this lecture. And all we have to do is make sure to click on the regression line box under plot options. One thing to say before we go any further, though, is it's only appropriate to use the best fit line to make predictions if a linear correlation exists. When there's not a linear correlation between the variables, the best prediction you can make is to just say that your prediction y hat equals your average y bar. Okay, so let's take a look at this example. The same set of examples that we've been using so far. It says, recall the data from example 2. We have number of absences, final grade. Calculate the line of best fit for the data in example 2. So let me take you back over to Art of Stat. We've got the data in there already. If we want the line of best fit, all we need to do is under plot options, click on regression line. And then it'll give you, not only will it plot the line, it'll sort of superimpose the line over our scatter plot, but it'll also give us the regression line, okay? Y hat equals 102 minus 3.62x. Okay, let's write that down. Okay, So part B asks, what would you predict the final grade to be for a student who missed class 10 times? Well, for that student, we would plug in 10 for x. And you can punch that into your calculator. Let's see, 102 minus 3.62 times 10 comes out to 65.8. So not great. Okay, that's a D. The student would have to repeat the course. So don't miss class 10 times for sure, right? Part C asks us to interpret the slope and the y-intercept. Okay. The slope here is negative 3.62. Okay, that means that every time we miss class, we expect our grade to drop by 3.62 points. Okay. As for the y-intercept, the y-intercept in this case is 102. And remember, this is what we get when we plug in 0 for x. So x is the number of absences. If we plug in 0 for x, that means we don't have any absences. We never missed class. So a student with perfect attendance expects to earn 102% in the class. Now, that value is actually not possible, right? You can't get more than 100% unless you have a teacher that offers a lot of extra credit, which would be, in my view, unethical. But that's another discussion for another time. But you know, the reason that we're getting such a large value is because notice that in our data set, we didn't have any students who missed class 0 times. So 0 kind of falls outside the scope that our model is good for, if that makes sense. So sometimes this happens, and sometimes you can end up with a prediction that doesn't really make a ton of sense, like this one. Okay. Let's look at number 8, right? It says, referring back to example 3, how many times would you predict that a person who makes $4,000 per month, or how many times would you predict a person who makes $4,000 per month to eat out in a month? Well, let's take a look at that data set, right? So this was the linear regression. This was the scatter plot for that data set, and we determined that there was not a linear correlation. So we could get a regression line, but it would not be appropriate to use it to make any observations for this data set because there isn't a linear correlation. So it's not appropriate to use the regression line to make our predictions. What we would do in this case is we would just say, well, the best prediction we can make, since there's not a linear correlation, the best prediction we can make is to just say that we expect them to eat out about the same amount as the average times that people eat out, which is about 6 times a month, right? We get that average here, okay? Or you could get it in Excel. So let's write that down. Since these variables are independent, the best prediction we can make is that y hat equals y bar, right? The sample mean for the number of times people eat out each month, which we saw was 6. So a person who makes $4,000 per month, we would expect them to eat out 6 times a month. If a person made $8,000 per month, we would expect them to eat out 6 times a month, right? Because it appears to be the case that your income level doesn't affect how many times you eat out in a month, okay? So that's that idea. I have 2 more examples here. These ones use larger data sets, so you're definitely going to want to have the data for 3.7 open here, and that way you can just copy and paste the data for example 9 into the linear regression app in Art of Stat. We're asked, so for number 9, the data there represent a random sample of 100 houses, the size of the house, and the size of the lot that the house sits on, both in square feet, are given. And we want to determine if there's a linear correlation between house size and lot size. The null hypothesis. You can actually run this test on your own, by the way. It goes without saying. You should pause the video, give this a try on your own. But I'm just going to go ahead and give you my solutions here. The null hypothesis is that rho equals 0. No linear correlation, right? The alternative hypothesis is that rho does not equal 0. There is a linear correlation, right? In fact, let me just write out that you could state these in terms of independence, right? This would be no correlation, right? House size and lot size are independent. Okay, and the alternative, that rho does not equal 0, right? There is a correlation. House size and lot size are dependent, right? Your let's say your lot size depends on how big your house is, something like that. You don't have to write the hypotheses out both ways, but that's how we would write them in terms of independence. Now we want to get the correlation coefficient. We're going to use Art of Stat to do that. And while we're there, we'll get the p-value. So we're going to go to Art of Stat. We're going to run a linear regression and enter the data, of course. And we'll see what p-value we get. So let's head over. So first of all, I need to grab the data. Actually, let's open up the app, linear regression app. And let me grab the data. I want to enter my own. You could upload a file, but you need a .csv, and I think that I have this as a .xlsx or whatever it is. So we'll just have to copy and paste. That's not a big deal. Control A, and then we'll copy. And then to paste, you can say Control V. Okay, there we go. Oh, I think I did that twice maybe. Let me try again. Control V so that I don't do it twice. All right. Oh, and actually I don't need the house size and the lot size in there. That'll mess things up. I wonder if I can remove that row now. Okay, because you just want the numbers in there. So we'll say submit data. Gives us this really nice scatter plot. Notice that we have 100 houses, okay, that we're comparing. And the x variable here was house size, And the y variable was lot size. So yeah, it looks like there's a correlation, right? It looks like as house size increases, lot size also increases. I'm not sure how strong the correlation is. It looks like the correlation coefficient is 0.534. So that's like a moderate correlation. The only way to know if it's really statistically significant, a statistically significant correlation, is to get the p-value. So I'm going to click on show standard errors and p-values. And yeah, look at that. For the slope, we have a really small p-value. So we would reject the null hypothesis. There's definitely a linear correlation here. While we're here, we might as well get the regression line. So let's click on that box. Since there is a linear regression, we could use this line to make some predictions about how, if your house is a certain size, how big will your lot be likely to be, right? Okay, so let's write this down. So our p-value was less than 0.0001. Oh, and our correlation coefficient R was 0.534. All right. .0001 is much less than 0.05. So reject H null. Oh, goodness. Reject H null. Okay. There is sufficient evidence to conclude that house size and lot size are linearly correlated. Or in other words, that they're dependent. Okay, linear correlation. Well, we already found this, right? For part B, we found this. It was 0.534. So then it says, determine the type and direction of the relationship between house size and lot size. Okay, because all we've done, we ran the test two-tailed. So all we've done is we've said there's a linear correlation, but we don't know if it's a positive correlation or a negative correlation. But looking at R here, R is positive. And that means that there's a positive correlation. That's the direction of the relationship. So there is a positive linear correlation. You can see that in the scatter plot as well, right? If you look at the best fit line, you can see that as house size increases, lot size also increases. The slope of the best fit line is positive, right? It's a positive number, 8.18. Okay, so if R is positive, the slope will be positive, and vice versa. If R is negative, the slope will be negative. Okay. Part C asks us to find the least squares regression line. We've already done that. Let's write it down. 6935 plus 8.18x. Part D says to interpret the slope and the y-intercept if appropriate. Well, our slope is 8.18, right? So and X represents the house size, right? Y represents the lot size. So if X represents the house size, well, we would say for every additional square foot in house size, we expect the lot size to go up by 8.18 square feet. Okay, that's the slope. The y-intercept is what happens when we plug in 0 for x. Plugging in 0 for x means that your house is 0 square feet, which could just be an empty lot, I suppose, right? So we might say we expect an empty lot, right? House size 0 square feet. So we expect an empty lot to be 6,934 square feet. Part E says, use the regression equation to predict the lot size of a 1,600 square foot house. Okay. It would be 6,934 plus 8.18 times 1,600. That comes out to 20,022. Okay, square feet. If you know anything about house sizes and lot sizes, then I think you would recognize that this is actually a very large lot. And a 1,600 square foot house is not that large. So there's something fishy going on. Maybe this is not in California. Maybe this is in Montana or something. I don't know. Somewhere where you would have very large lot sizes, I suppose. That's that idea. Okay, let's look at one more. For example 10, the data represent a random sample of 60 university students in Florida. The students' ages along with the distance from their home to the university in miles are given. Determine if there's a linear correlation between age and distance, right? Age and distance that the university is from home. Null hypothesis is that there's no correlation. Rho equals 0. Alternative hypothesis is that there is a correlation. Rho does not equal 0. Step 2 is to get the correlation coefficient, which we're going to get in the same place as we go to get the p-value, art of stat. We're going to do a linear regression. And of course, we're going to enter the data. And then we can get a p-value. So let's see. So let me open up a clean app. We want to enter our own data. I'm going to grab that from Excel, example 10. Control A to grab it all. Copy. And Control V to paste. And X here. what was this first variable? Age. X represents age. And Y represents distance. Okay, we'll submit the data. And wow, that doesn't look like there's much of a correlation at all. Our correlation coefficient is pretty close to 0. Only way to know for sure is to show the p-value. And the p-value for our slope is pretty large. Okay, so probably not a linear correlation here. Let's write it down. So our p-value is 0.3695. Our correlation coefficient was 0.118. So let me write down my reasoning. 0.3695 is not less than 0.05. So do not reject the null hypothesis. Okay. There is not sufficient evidence to conclude that age and distance from home to school are linearly correlated, or in other words, dependent. Okay, there's not sufficient evidence to say that they're linearly correlated, or in other words, dependent. Okay, part B asks us to compute the linear correlation coefficient. Again, we already got this, but it was 0.118. It says, what kind of correlation, if any, exists between age and distance? There is no linear correlation. So then part C asks, about how far from the university would you expect a 20-year-old student to live? And because there's no linear correlation, we're not going to use the regression line to make that prediction, because there is no linear correlation. So it doesn't make sense to use the regression line to make that prediction. The best we can do is to just say, well, we expect a 20-year-old to live the average distance from the university, right? 3.82. And then part D is going to ask, how far would you expect a 30-year-old student to live? And we'd say the same thing. We expect them to live the average distance from the university, 3.82 miles. So let's write those down. We expect the student to live 3.82 miles away. And the same thing for part D, right? We expect the student to live 3.82 miles away. And again, that's because apparently age doesn't affect how far from the university you live, right? And so we expect the expected value, y hat, is just equal to the mean, y bar, which was 3.82, right? And same thing here. Okay, so that'll do it for examples. Now, I said in the last lecture that I would spend some time talking about this idea that correlation doesn't imply causation. And it is an important topic that we need to really discuss, right? So let me just give you a couple examples, right? It is the case that both teenage birth rates and homicide rates have been declining since 1993. So there is a correlation between teenage birth rates and homicide rates. But that doesn't mean that teenage birth rates declining causes homicide rates to decline, right? It doesn't mean that just because teenagers are getting less pregnant or are getting pregnant less often, that somehow people aren't going out and murdering people. Like, there's obviously no causation there. There's no causal relationship. So there's a correlation, but it's not necessarily a causal relationship. Another really good example of this is about kids enrolled in music programs. There used to be this thing when I was in school, and I was a band kid, so I did band all throughout school. My dad was a band teacher. And so, but there was this thing in like the 90s where people thought that, people thought that that if you were enrolled in music, then you were going to get smarter and you're going to have a higher GPA. And that's because there was a correlation between kids being enrolled in music programs and kids having higher GPAs. And so they saw that correlation and they thought, oh, wow, music must make people smarter. But it turns out that that's actually not the case. When you try to verify that through experimentation and you take kids and you start to teach them music, their GPAs don't just magically increase from that. But people had all kinds of theories worked out where they thought, oh, well, maybe it's because music is like a right brain activity or a left brain activity, and math is like a right brain activity. And, maybe if you're exercising both hemispheres of the brain, that helps your entire brain to work better or whatever. But it just turns out to not be true. It's just not backed up by the evidence. So then that kind of leaves the question, well, why is it that kids enrolled in music programs tend to have higher GPAs? And you might think of a lot of different answers to that question, but I think the answer that I would give is that, well, if you're a kid who's enrolled in a music program, it's probably because you have pretty involved parents, okay? Because no kid is going to sign up for piano lessons of their own volition, right? If you're an 8-year-old kid, like, that's typically not something that you just gravitate towards. Usually, if you're a kid who's enrolled in a music program, it's because you have very involved parents. And if you have very involved parents, then you're probably also going to have a higher GPA because your parents are going to be making sure that you're getting your homework done, right? That you're doing all of your studying, and so on and so forth. So it's not that music makes you smarter. It's that if you're enrolled in music, you have involved parents. And so then you also probably have a higher GPA. By the way, this doesn't mean that if your parents didn't enroll you in music programs that you're not loved or something, but that's the idea. So correlation does not necessarily imply causation. And again, there's a link here that you can follow that I think has some really funny ones, like apparently the number of drowning deaths in the United States is correlated with the number of films that Nicolas Cage has starred in, right? And things like that. But clearly there's no causal relationship there. So I'll let you click that link and kind of look through some of those if you want. But that's all I have to say on the matter. And thank you for hanging in there this long. We'll check in with you in the next lecture.